Good morning, good afternoon, or good evening. This is a full paper workthrough of the 2024 AS Paper 1, the pure paper for further maths. And this is going to be, well, I have seen the paper already, but it's going to be mostly a blind look through to show the kind of thought processes and ideas to tackle a paper like this. As you come to the end of your revision, this is the way you should be tackling these papers to best prepare yourself. So let's jump straight in. We have our question 1, straight in with hyperbolics. Express cos squared in terms of sine squared. So we're looking for that Pythagorean style identity. For trig, it's sine squared plus cos squared equals 1. If you remember the trick which swaps the sign of sine as it turns into shine, we can remember that our hyperbolic identity is as so, which means rearrange it to make cos squared the subject is 1 plus shine. Question 2. The function is given as so. We're going between the enclosed by f and the y-axis. So we have our function doing something like this, starting at 3, between 0 and 5. We want the region rotated 2 pi around the x-axis, so it's going to be a dx. And we remember our formula is pi y squared dx between those limits. So I'm looking for, well, those have got 2 pi, so they don't work. That one doesn't have the squared, so that's one with the correct formula. Question 3. A matrix is such that the determinant is 2. Determine the determinant of the inverse. Now this is a general fact that the determinant of the inverse is 1 over the determinant of A. Best way to justify that is the determinant of A times the determinant of A inverse. Determinant is what we call a multiplicative function, so you can put the multiply in between, which is the determinant of the identity, which is just 1. So they are inverse of one another, so the determinant of A is 2. The inverse determinant is a half. We now have our vector line. We need to turn this into the Cartesian form. And that thing goes on the top of the fractions, swapping the sign. That thing is your denominator, so I'm looking for a -9 on the denominator of the first one, a 1 and a 3. So it's one of the first two, but let's at least do the top one. We have to swap the sign as it comes out of the position vector. So there's that one there. Okay, that's multiple choice questions done very efficiently. Question 5, you've got another vector. Calculate A dot B. Well, I prefer to work in column vectors, so I'm going to rewrite A as a column vector and B as a column vector. And then the dot product is the top multiplied 3 times 2, the middle multiplied, and the bottom multiplied. Then add those 3 products together. A bit of mental arithmetic. Now we get 12. Calculate mod A. Well, mod A is the Pythagorean trick. Is you square them all and you add them together. I've dropped the negative sign on that last one. It doesn't make any difference when you square a negative, it becomes positive. And this is where I'm going to grab my calculator. I'm not going to risk misadding so many things together at the same time. That comes out as root 29. Same for B. And notice I am trying to make it really clear to the examiner that I know what I'm doing. This one I can do a bit more easily without the calculator. That comes out as root 30, surprisingly close. And if you did have the time at the end to check this, you can draw those two lines either in your calculator or on paper, and you should hopefully see that they do look similar in length. So then we want the acute angle. Well, A dot B equals mod A mod B cos theta is the other form of the dot product. So therefore cos theta equals A dot B over mod A mod B. And we just need to cos inverse that. Calculator says nearest degree, so I'm going to change my angle in my calculator to degrees, and then it's cos inverse of 12 over root 29 root 30. Making sure that I get things in the right places, and that's giving me 65.993, etc. It's a good habit to always write out many more degrees of accuracy than the question wants, and then round it afterwards. Just a safe way to ensure you get the marks. Sketch cosh x, or cosh was the half e to the x plus e to the negative x, which means it's always positive, and this is our steep quadratic. My apologies, that was a sneeze break. Solve the equation cosh x equals 2. Give your answer to 368. Now I'm going to check the number of marks here. If it was more marks, I'd have to do this by hand. Because it's so few, I'm actually just going to look in the formula book, because I know there is, and I've pulled up just a normal maths one. Let's pull up the further maths formula book, because I know in there we've got the Lund forms of the inverse hyperbolics. You could memorize them, but even if you have, it's worth checking that you haven't misremembered them. So they are here. So they're on page 8 of that formula booklet, and from that we have that cosh inverse of x is equal to ln x plus the square root of x squared minus 1. We want the cosh inverse of 2, so going for ln of x, ln of 2 plus 2 squared minus 1 is 3. But the thing you need to remember with that formula in the formula book is it only gives you the positive solution. If we look at the graph, we're solving cosh x equals 2. There are 2 solutions, so we just need to remember to include that second solution. And by symmetry, the graph is just a negative answer. 2 marks is all that's worth. If you're doing more work than that, you haven't remembered the formula book exists. Question 7, a mean value question. The function is that between that, give your exact answer in exact form. So exact form implies that we can't cheat too hard with our calculator. It is 3 marks, so maybe the calculator does give it exact and we can be cheeky. So the mean value is given by the formula 1 over b minus a integral between b and a of the function. So now we just need to put the numbers in. B was 7, a was 4, so it's a third of the integral between 7 and 4. I'm going to rewrite the f as x to the negative half. This is an easy integral, so I'm just going to do it by hand. Increase the power by 1, divide by the new power between 7 and 4. Now I can see why it's going to need exact form, because I'm putting a 7 into a square root. So that's going to be 2 root 7, sub in the 4, minus 4. I could probably leave it like that, but I'm going to put it as 2/3 root 7 minus 4 over 3. And again, good technique, as soon as you have an integral that you can solve, you should do it in your calculator even if you didn't intend that to be your main technique. So I've done it all by hand, but I'm still going to type into my calculator the whole thing. So my upper limit is 7, my lower limit is 4, And yeah, my calculator didn't give it to me exact. So you can get around that when you're checking by typing in what you think the answer should be and comparing it. So I'm going to also type in my answer and just see if the two lines are the same, and they are. So I'm almost guaranteed to have got this right unless I've misremembered or misquoted the formula in some way. The next question. Complex numbers now. Write down the complex conjugate Z star. Bit of memory what the complex conjugate meant. It's just the same but with the opposite imaginary part. Hence proves that ZZ star is real. Be warned of that word proof. We do need to make sure that we argue carefully. No skipping of steps, no cheating. Now to start with, all we're doing is a bit of FOIL, expanding out brackets. I am going to do this last bit slower. I'm actually going to write in that I squared, and then I can get rid of it. I'm going to put a little comment on the side as I squared equals -1. So I wouldn't normally do that for any algebra, but because it's a proof I have. And then I've got that, which is real, as x and y are real. So you take two real numbers, you square them and add them, you're going to stay real. So I've proved there that ZZ star is real. The complex number satisfies that equation. Find W. We have choices here. We could try and do some really smart things because of the previous part of the question. One instinct I had was to multiply the whole equation by W star. That's not going to be useful, but I just wanted to make a W star because the previous question. That's not going to help, so we're not going to do that. The much better technique is just to replace W with the complex form and sub it in. So we've got 3x plus 3yi plus 10i, then 2x minus, because it's the conjugate, 2yi plus 5. And then we can compare real parts and imaginary parts. The real part is saying 3x on the left has to match with 2x minus 5, which means x equals -5. And the imaginary parts, the left-hand side imaginary part is 3y plus 10. The right-hand side is -2y. Notice I don't put the i's. When you consider the imaginary parts, you're looking at the coefficients. Now this one requires just a tad more work. 5y equals -10. So y equals -2. Now I haven't answered the question. It wanted W. I made up some more letters, so I need to go back to W. And once again, because we've got these really clever calculators, we can check this very easily. We can type in 3 lots of -2. Oh, there is a special I button. Why have I got -2? 3 lots of -5 minus 2i plus 10i, and that gives me one complex number, and I can do the same to the opposite side, 2 lots of -5, but this time we're adding 2i, and then add 5 at the end. Those two things aren't matching right now. So what have I done? So that my left and right side of my equations aren't the same. That feels like I've made a sign error somewhere. I have. And this is why you do the checks. This was a plus here, turned into a minus there. So this shouldn't be -5, it should just be +5, which means that it's +5 there. And that's also a good habit if you do make a mistake. Well, one, do your mental checks, but two, when you make your corrections, don't cross out so it can't be seen what's underneath. Just put a simple line through. It's useful for the examiner, and they might be able to give you some kind of method marks or credit. Find the value, finally, of omega squared w squared, w star squared. And I'm actually going to write that in a slightly different form because of what happened earlier in the question. I'm going to write that as ww star squared. And then ww star, we've already worked out what that looks like from the previous part of the question. It was just the x squared plus y squared. And this way, I don't need to be dealing with I don't need to multiply complex numbers together at all. I'm just doing numerical work. That's only 1 mark, so maybe I could have even done that in my calculator with doing no calculation at all. Question 9, we're now on to our method of differences style question. We're going to start with our partial fractions. Now you could go from the right to the left or the left from the right. I'm going to start with the left-hand side. There's a lot more to do with that side. So my left-hand side, I'm just going to recreate the question. And then to be able to combine them, I need to make a common denominator. So I times the bottom, the first one by r plus 1, so the numerator needs to be times by r plus 1. The second one I've times the denominator by r plus 2, so the top gets an r plus 2. So expanding out, making sure that I'm careful that I'm subtracting the entirety of that second fraction. The biggest issue with questions like this is sign errors. And the r squared cancels with the r squared, the 2r cancels with the 2r, and I'm left exactly as the question wanted, equals right hand side. And I like to put a little as required on the end. If you want to use QED or a little box, all fine. And that was only 1 mark, so I've probably gone into a bit more detail than required. Use the method of differences. Well, the thing we're summing is exactly what we had in that first part. So I'm going to rewrite it, not using the sum that they've told me, but the sum, I've written as an r plus 1 over r plus 2. This is the partial fraction form. It's not really partial fractions though, is it? Because you've got r's on the top and the bottom. That's a bit of a misquote. The separated, clever separation fractions form. And then I'm just going to write out the first few terms. So when r is 1, this is 2/3 minus a half. When r is 2, that's 3/4 minus 2/3. Then it's 4/5 minus 3/4. So we're starting to see the pattern. I'm going to go dot, dot, dot. I'm going to do the last 2. So when r is n minus 1, and n minus 1 over n. And then finally at n, which is just exactly the same formula, but with n instead of r. And now I need to look for what's cancelling perfectly. And almost always it's these diagonals that cancel. And now I don't see the n minus 1 over n, but I know it had to live in that spot just before. And in the same way, I didn't see the 4/5, but I knew it had to live in that spot. So I can cancel it out even though I haven't written everything. So what's left behind? Left behind is the n plus 1 over n plus 2 minus a half. So that was that term, and that term still live, making sure that you are respecting the fact that's a negative a half. So now I need to simplify it. I'm expecting the next page to actually have working space, but I'm not going to use it. Times top and bottom of that by n plus 2. I need times top and bottom of this one by 2. So I've got 2n plus 2 on the numerators. So that becomes 2n minus n. That's 2 minus 2 on the numerator, so that's fine. On the denominator, looking back at the question, it did want to expand it. N over 2n plus 4. Now if I wanted to check this, I could try some small values of n. If I put n equals 1 into this, the summation, where you're just adding one term, the summation side of the formula is giving me 1 over 2 times 3 is a sixth. And if I put it into the n over 2n plus 4 form, 1 over 6. If you're still not convinced or you've got more time to check your work at the end, you could also do the sum of the first 2 terms and check that that matches the formula. I'm going to leave it with that check for now. Hence, find the exact value of that thing. Okay, well, the first thing to notice is we don't start at 1. And almost every formula that you create starts at 1. So we need to manipulate this. We need to be smart about this. And the best way to do that is to treat this summation as a sum from 1 to 2000. We need to get up to 2000 somehow, but then subtract off the stuff we don't want. But if we want to start at 1001, we don't want the stuff up to 1000. So we're going to do a subtraction of 2 formula. Now both of these formulae look exactly like what we've discovered in the previous part. So these are the n over 2n plus 4, and the same for the other one, but with 1000, 2 lots of 1000 plus 4. Hence is a key word here as well. I am a big fan of the word hence. And then I'm going to hit these into my calculator. 2000 over, I'm going to write 2 times 2000 plus 4. I'm going to work that out before. Over 2004. So that's a horrible number, but relatively symmetric. That's quite a nice denominator. 501 501, 501. That's an incredibly small number. So my instinct is, does this seem reasonable? Am I supposed to be summing 1,000 terms and I still get something which is less than 0.0001? Well, 0.005 if you turn that into a decimal. And yes, I think so. Because all of these 1,000 fractions, the denominator is at least 1,000 times 1,000 is at least 1 over 1,000,000, which is 10 to the negative 6. And they get smaller. And this is roughly, very roughly, because the calculator told me, 5 times 10 to the negative 4. So that does seem reasonable. A surprising looking number, a very small number for a summation, but actually seems reasonable. Question 10, are rational functions? The curve shows that with its asymptotes, it hasn't told me what the asymptotes are, but it tells me to write them down. So our asymptotes, our horizontal asymptote is when the denominator fails. Well, that's going to be x equals, no, this is my vertical one. My vertical asymptote is my x equals asymptote, is where the denominator is a divide by 0. So that's at 5/3. And my horizontal asymptote is when x tends to infinity. When x goes to infinity, that minus 10 and minus 5 don't matter. So my horizontal asymptote is y equals 2/3. Okay, we have a new line, y equals negative 2/5 plus 2. So plus 2 is telling me it's going through there. Negative 2/5 means it's a sloping downwards. I do want to check where it crosses the x-axis, because at the moment I don't know if it goes there before the asymptote, it could go there after the asymptote, it could even go all the way over there and go through that 5 or beyond. And saying that, I think it's going to do something special. So when y equals 0, I'm solving 0 equals negative 2/5 x plus 2, which is indeed when x equals 5. So it's actually going through perfectly the 2 intercepts. Now, of course, with the pencil ruler on an exam, you can make this line a lot nicer, and I keep missing. It needs to be slightly shallower than I think it is. There we go. So that's my line, and I'm going to call it L. Question called it L. Hence or otherwise, solve the inequality. So that's really saying that C is below L. And it's quite nice because I already know the x values where these two things intersect. So that was really smart of the examiner. So where is the curve below the line? The curve is below the line from here and back, and in this region here. So I need to describe those two regions. So that's when x is less than or equal to 0. I'm allowed to be 0 because it was less than or equal to inequality. I need to be less than 5, but I need to be bigger than that asymptote, which was 5/3. And 5/3. Now the asymptote inequality has to be a strict inequality. You can't sub 5/3 into that inequality. It's not true at 5/3, so that has to be strict, even though that was a less than or equal to in the middle. Okay. Question 11. Complex matrices. But all we're doing is finding the product. So although we've got complex numbers in here and algebra, all we're doing is multiplying two matrices. Now they had to put that algebra A in so that you didn't cheat in your calculator and just type it out. So let's multiply it out. We're going to do top row times first column. So that's going to give me a 12i plus 4i, that's 16i. And the second set, the first row times the second column, 15i plus 2 for a. And then we've got a minus I times a minus 2i. So that's 2i squared or minus 2. And finally 5a plus I. Now if you're not as confident multiplying out matrices, you should do that in a lot more steps. If you're not as confident with complex numbers, do it in a lot more steps. Now you can check this one. Best way to check a question like this is to pick a value of a. Just randomly pick a to be 4. Type it into your calculator, see if it works with your answer being with a is 4. And you can get a good check, and again, you can almost guarantee that you got the question right, or go and find your mistake to correct it. Question 12, proof by induction. Now, I want to prove this in a different way. There's a really sneaky factorization trick which will prove that this is divisible by 3 in roughly 20 seconds. So I might show that at the end of the question. But the question told us to do induction, so let's do it. So the base case, when n equals 1, 5 to the 1 minus 2 to the 1 is just 3, is a multiple of 3. Sorted. The inductive step. I'm going to assume 5 to the k minus 2 to the k equals 3m for some integer m. So that's what it means to be a multiple of 3. You are equal to 3 times something, and then I'm going to consider 5 to the k plus 1 minus 2 to the k plus 1. And now I need to try and manipulate this thing to forcibly use that 3m in some way. Well, the only thing to do first is to bring down one of the powers. So rules of indices say we can bring down, or we can separate an addition in the power to a multiply. So that's 5 to the 1 times 5 to the k minus 2 times 2 to the k. And now I can see that this 5, I can split into a 3 and a 2. So I can write this as 3 lots of 5 to the k plus 2 lots of 5 to the k minus 2 lots of 2 to the k. So that's 3 lots of 5 to the k plus 2 lots of, surprise, surprise, that's the thing we already know. So that's 3 lots of 5 to the k plus 6m. Make it really obvious that that is a multiple of 3, and we're sorted. A multiple of 3. Because of the inductive step, we use the inductive hypothesis from there to say that 5 to the k minus 2 to the k is a multiple of 3. So now we just need to write our conclusion. So therefore, as n equals 1 is true and n equals k implies n equals k plus 1, the 5 to the n minus 2 to the n is a multiple of 3 for all natural numbers n by mathematical induction. Now there's lots of different ways to write that conclusion, but you have to put the phrase mathematical induction in there somewhere. You have to say that you've done the base case, you have to say you've done the inductive step, and you have to throw the statement in there, so you can't really get more efficient than that. Now I did kind of promise that there's a much easier way of doing this, and you can actually factorize this thing just like a difference of two squares, but not quite. And I believe the factorization is as so. That's not an n plus 1. It needs to be an n minus 1 in the power. I'm not going to justify it too much, but this can be factorized into a potentially a very huge thing as so. And if you were to try and expand that back out, you'll see that absolutely everything cancels out. Oh, I misquoted the question. Oh no, that should be a 2, not a 3. I'm not going to rewrite the whole thing. But imagine that all of my 3's in that final statement are 2's. If you were to expand it out, everything cancels perfectly, and then you'll be left with the 5 minus 2, which is 3, times by this horrendous bracket, so you get it's a multiple of 3 automatically. Which is why the question had to say, and as the questions always do say, by mathematical induction, there's almost always another method. Question 13, this is our roots of polynomials question. We have our roots. Our cubic has roots alpha minus 1, beta minus 1, gamma minus 1. The coefficient in P is also 1. Describe the transformation that maps it. So the roots were at alpha, beta, and gamma. All of the roots have moved 1 to the left. So the whole graph had to move 1 to the left. So translate by -1, 0. And therefore, well, a translation by 1 to the left is changing x to x plus 1, which is also the technique if you use the kind of the magic W method. You would get that x equals w. Sorry, no, other way around. The new roots of w are the old roots minus 1, and then you replace x with w plus 1. But that's the same that we get from the transformation here. So therefore, p of x is the old function, but the x has been replaced with x plus 1. We should write this out, so I am going to expand this out. I'm going to use what I know about Pascal's triangle to really quickly expand that out. So I know Pascal's triangle is 1, 3, 3, 1 on that row. And then collect like terms and sort it. Now you can check this. If you, in your calculator, solve that cubic, you subtract 1 from one of the roots and you sub it into our new p of x, you should get 0 still. A nice way to check it again. And just more working space. Question 14. Matrix transformations, maybe? Yeah. Transformation is given by that A has that coordinate, find the coordinates of the image. Well, the image is just m times the coordinate. So I'm trying to do the multiplication. Matrix times 4, -5. And I could do this in my calculator, or I could just multiply it out. 3 -1 times 4 -5 is 12 plus 5 is 17. minus negative 38, I believe. Yeah. Again, do that in your calculator, and in your checking time, definitely do it in your calculator. Show the only invariant point under t is the origin. So we should remember that the origin is always an invariant point, but sometimes for certain transformations there are more. So to be an invariant point, when you get hit by the matrix, you don't move. So m times the point is still the same point. Expanding out the left-hand side as so, and that has to match the right-hand side. So this is giving us two equations, 3x minus y equals x, which is saying that 2x equals y, and minus 2x plus 6y equals y, which is telling me that 2x equals negative 5y. Well, if I combine those together, that's telling me that y equals negative 5y, i.e. y must be 0, and then x must be 0 from 2x equals y, so 2x equals 0. So therefore, 0, 0 is the only invariant point. Now you could have solved those simultaneous equations in your calculator as well. I don't know if my hand is just as good. It's a show, that question, so I want to be as clear as possible. Part C. The line y equals x plus 1 is transformed to a new line. Find the equation of the new line. So this is quite awkward. This isn't something that we do very often. And we have to try and make our own method for this a little bit. So let's make sure I quote the matrix right. 3, negative 1, negative 2, 6. So if I want to show that a line maps to a line, I'm going to have to hit a general point on that line. Well, a general point on that line, if we give it the x-coordinate x, the y-coordinate is x plus 1, because y equals x plus 1. So let's see where a general point on line 1 goes to, and then decide afterwards what the best rest of the technique is. So I'm going to do this one a little bit slower, mostly because I want to give myself some time to think what is coming next. How am I going to do the next part of the question? And I'm really hoping something, it's not immediately obvious. I was hoping that this y coordinate was maybe just double the x coordinate. And then I can say, well, it's y equals 2x. And then I'll be happy. Well, that's what I know I can do. So let's do exactly that. Let's try and do something to transform the x coordinate into the y coordinate. Well, I can double it. That'll get me to 4x minus 2. But then I need to add 8 to make the minus 2 that I have into the plus 6. So I think the line is simply 2x plus 8. That is the way to turn 2x minus 1 into 4x plus 6, no matter what x is. And that's the important bit. This has to be true no matter what x is. Now that might seem a bit magical, and certainly for 5 marks I seem to have already got the answer. If you wanted to be a little bit more rigorous with this, you can call L2 y equals mx plus c. We know what, well, I should really say new x and new y. We know that the new y is 4x plus 6 is m2x plus 1 plus c. And now this is feeling very much more like the invariant lines, a line of invariant lines method. And now the coefficients have to match up. This is a identity. This is true for all x. True for all x. which means coefficients match up. Looking at the x coefficient, 4 equals 2m, which means that m equals 2. What a surprise. I've got a 2 up there. And then 6 equals m plus 6. Aha, I've spotted a sign error. That should be 2x minus 1. Transcription from above. Again, I was expecting a certain answer. I didn't get a certain answer. That's negative m, which means that c equals 8. And we get the 2x plus 8. M is 2, c is 8. In a slightly more rigorous manner, rather than just forcing it to work. If you do break down my argument to get to those two things, it is exactly the argument that we've got here, just without writing everything out in glorious detail. A really nice question in the end. New, I don't think I've seen something like this before, but using techniques, adapting techniques we have, makes it work. Maclaurin. Use Maclaurin's series for 1 plus x, ln of 1 plus x, to do that thing. So, first thing I'm going to do is jump into the formula booklet and find the ln x. Now I only need to go to x cubed. So I'm only going to go up to x cubed. So ln of 1 plus 3x. I'm replacing the x with 3x. Oh, missed a squared on that. Because it's a show that question, I am going to do the simplification in 2 steps, even though I can quite quickly see that I'm getting what I want. So that's 3x. That bracket becomes 9 over 2x squared. That's going to become 27 over 3, which simplifies. Okay, that was only 1 mark, so I've gone a bit crazy, but that's okay. Julia is attempting to find a series expansion to use an approximation for ln 4. Her incorrect working is as so. So she's tried to work out what value of x would make the 4, and then she subbed that value of x into the answer above. Now that looks reasonable until we look back at the formula booklet and realise that there is a restriction of what you're allowed to sub in. So ln of 1 plus 3x is only valid for, now in the formula booklet it says that x is between -1 and 1, but our x is a 3x, so between -1 3x is less than or equal to 1. I quoted that directly out of the formula booklet. So x must be between 1 and 1/3, but Julia used x equals 1 outside the valid range. No go, not allowed. That series, if you go on forever, will not converge. It'll end up diverging, which basically means it's not going to work. It's going to get further and further away from the value. And actually, if you type into your calculator ln 4, it's about 1.38, which is not 7.5. So she's used something outside the valid range, and therefore the summation just does not work. Now the question is telling us to use x equals -1/6. Now -1/6 is in that range that we've just described, so that's going to be valid. So because it says fully justified, I'm actually going to write that first. X equals -6 is in the valid range for the expansion. I'm not expecting to get a mark for that, but it's worth saying. So what does that actually give me? So ln of 1 plus 3x, well, that's ln of 3 times -6 is -1/2. That's ln of 1/2. Is that correct? I'm going to type that into my calculator because I don't trust it. Times 1 over 6. Yeah. So this is negative ln 2. I care about ln 4. So this is negative a half ln 4. Because 2 squared equals 4, I want to put a 2 up as the power, but I can't just randomly put a 2 there. I need to counter it, so I need to counter it by putting a half. Okay, so from part A, negative a half ln 4 is roughly the 3x, and I'm going to need to remember it, plus 9 over 2x squared plus 9x cubed. Let's check I've quoted that correctly. 3x minus 9 over 2x squared plus 9x cubed. Brilliant. So that thing, and notice that I've used the roughly equal to on the first line, but not on the second line, because that first line is exactly equal to the second line. But the left bit, the negative a half, is not the same. So you could use roughly equal to all the way down. I didn't. And my calculator's told me that's negative 5/12. So therefore, ln 4, which is, I'm really quite happy that this came out being negative, because I know that ln is positive. If this thing here did not be negative, I would get ln as being negative, and that's sad. So now I need to times 2 by negative 2, so it's roughly 5/6. Now that doesn't feel like a very good approximation. We already said that ln 4 was 1.38, and I'm saying it's actually 0.83. That's not a very good approximation at all. Now we have only used the first 3 parts of the series expansion, but I am going to take a moment just to check that I haven't done anything silly. So I checked that, which is the negative 2. I'm also going to check that negative a half ln 4, negative a half ln 4 is the same as ln half, which they are. The calculator agrees that they're the same, so that point's fine. I've already checked that I pulled the question from the previous page correctly. Just going to check I subbed it in, didn't do anything silly with the negatives. Yeah, that seems to match. I wouldn't be surprised if there's some error there, but I've done the checks and I haven't found an obvious error, so I'm going to move on. Question 16, we have a lovely polar curve. When I say lovely, that looks horrendous. Show the Cartesian equation can be written in that form. So the couple of things that we need to remember is r equals x squared plus y squared, or r squared equals x squared plus y squared. X equals r cos, and y equals r sine. So what's the best way to tackle this? Well, I don't have an r squared. I've got a lot of other things going on. So I'm actually thinking I'm going to multiply up. So I'm going to have r root cos squared plus 4 sine squared equals 2. I want the squares involved, so I'm going to square the whole equation. So I've got r squared, which is cos squared. R squared cos squared plus 4 r squared sine squared equals 4. And now I can use these two, which gives me x squared plus 4y squared equals 4. Dividing through by 4, x squared over 4 plus y squared equals 1. So a equals 2, b equals 1 in the form that they have. So that's an ellipse. Nice. The second part, hence sketch. So straight away I've spotted that that is an ellipse. And we do have that in the formula booklet just as a standard form. It doesn't actually give us anything more useful, unfortunately. So that's an ellipse. A couple of things that we should do is find the intercepts. When y equals 0, x squared equals 4. So x is plus or minus 2. and the other way around, if x equals 0, y squared equals 1. So I'm actually going to draw the ellipse first, and then I'm going to put those intercepts on. But from that little calculation, I know it's a fatter circle. So that's -2 and 2, that's 1 and -1. Now with fine pencil and ruler, I'd redo that. The bottom of my ellipse is a little flat, and my right hand side isn't perfect. For now, we'll leave it be. Question 17, loci. Circle represents the locus of points. So straight away, I know that the centre of this circle is positioned at AI, and B is the radius of the circle. Well, straight away, I'm looking down at the question now. Write down the value of A, halfway between 2 and 8, has to be 5. Do I need to write down the value of B? I do. So B is the radius, is going to be 3. Either the difference halved between 8 and 2, or the difference from 5 to the 8 or 2. So I'm just going to do a little check that Z minus 5i equals 3 would indeed give me that circle. Yes, it does. When I put 8i in, it works. When I put 2i in, it gives me the opposite side. Happy days. The half line, L, is represented by the argument is tan inverse of K. Now, the nice thing about that is this angle here, therefore, is K. Let's do a quick check. That's the opposite. That's y over x. Tan of that is y over x here. Where K is positive constant, the point P is the only point which lies on both of them. O represents the origin. Calculate the length of that. So we need to try and find some kind of right-angled triangle that will get us what we want. Almost always the centre of the circle is a brilliant place to go. So I think that there is a right-angled triangle which I'm going to focus on. I'm going to call the centre C, and I'm going to draw that triangle over here. So that's OPC. I know that OPC is a right angle because a tangent meets a radius at a right angle. I know that C to P is a length of 3 because the radius was 3. I know that O to C is a length of 5 because the radius is 3 plus 2, or even the centre had a y coordinate of 5. And it's asking me for OP. This is a really difficult way to ask for Pythagoras. So it's a shorter side, subtract that equals 16, so the length OP equals 4. I'm expecting the next part to find K, calculate the exact value of K. So K is that angle there. Maybe the best way is to look what other angles are similar to K. So I believe that angle there is also K. If that's a right angle, then that one there is 90 minus K, so the other one is K. So the next part of the question is now asking for that top coordinate. So a bit of SOHCAHTOA, we have the adjacent and the hypotenuse. So we're going for K equals cos inverse of 3/5. Now cos inverse of 3/5 is not exact. If we were to type that into our calculator, we will not get an exact value. I think it's either 36.9 or 63.1, I think, is the combinations for that triangle. So exactly is the cos inverse of 3/5, so we're going to leave it like that. Find the complex number represented by P. Okay, so now we need to actually create the P. So the P is there, the angle there was K, and we've worked out the modulus is 4. So we need to find the x and the y coordinates. So x is 4 cos K. Well, cos K is 3/5. So that's going to be 12 over 5. And then y we can do as a sine, or we could do Pythagoras again. So that's going to be the square root of 4 squared minus 12 over 5 squared, which is going to be something nice, I hope. Where's my next line? 4 squared minus 12/5 squared square root. Oh, this calculator doesn't like just hit equals. Okay, and that gives me 16/5. Which we're expecting something nice. So the coordinate of P is the x coordinate plus the y coordinate I. And we're done. That was the very last question on that paper. Now, as you do your own revision, you will then go back and check every question. I've spoken a bit about the mental checks that work well, looking for ways to confirm that your answer was correct by subbing things back in, looking for the key sign errors, etc., having a bit of intuition. So particularly on that summation question, that series question, noticing that 5/6 doesn't quite feel right. If there's any question in the paper which I'll do again because I don't feel right about, it'll be that one. The rest of them we've kind of confirmed either by doing it in two ways or the question implies that we've got it right just by the way the question is worded. So I hope this is useful. If you do spot any errors that I've made in here, feel free to let me know. Otherwise, happy revising.